divided into outer and inner crust. Similarly, the core is divided into outer and inner core. And in the inner core, density is so high, a few times the normal nuclear matter density, and all sorts of exotic things could happen there, hyperons, bosons like condensates, quarks, all this stuff could appear there. Okay, I just mentioned here this inner crust actually contains nuclear clusters and free neutrons. These free neutrons are in superfluid state. That means it is very straightforward in nuclear physics that two neutrons actually they fill the attractive interactions because it is coming out of nuclear physics. It is not like the super pair forming by two electrons actually, where one has to invoke this phonon actually mediated their attractive interactions for them. So in the talk actually, it a little load talking about this some discussions with Professor Sinha about this nuclear matter and superfluidity. So there this superfluidity appear actually, and as well as the superfluid would appear in the core. But I will actually trace on this inner crust, this superfluidity of the inner crust in the next slide. Okay, before after crust I will. Okay, so what you see on the y-axis is binding energy per particle of various nuclei in the in the outer crust. So mostly these nuclei are bound, but when their binding reaches around or when actually this nuclei became more neutron rich, these neutrons drift out of this nuclei, and that is called the tipping point, and that is the end of the outer crust and the beginning of the inner crust. Okay, so go to the inner crust. So what you see here in this inner crust, these are not nuclei which are available on the Earth. These are basically, you can see these mass numbers quite high, 1300, 1200, so on. So why it is so? These are nuclear clusters mostly made of neutrons. And think about this statement of Landau, what he said, this gigantic nucleus, all nuclear marching into a gigantic nucleus. So indeed it is happening here actually. Okay, on the superfluid point, so this superfluid is rotating by forming an array of quantized vortices. Now this neutron star crust has a crystal structure. So at the lattice sides, all nuclei or nuclear clusters are sitting, and this vortex lines are actually pinned to this each actually nuclear sites. Now in the bottom picture, you see this angular velocity as a function of time, and two angular velocities are shown here. One is neutron star actually, it is spinning down, so its angular velocity is decreasing, which is denoted by the green line, and the superfluid actually, which has a denoted by here by this red line, and these are pinned to the nuclear clusters. Now this nuclear superfluid actually angular velocity cannot actually catch up with this omega. So this difference is increasing, and there will be a critical lag actually when all these pinned vortices will be free. They will give their angular momentum to the crust, and as a result, suddenly this neutron star will spin up. This phenomena is known as glitch phenomena, and this happens in younger pulsar, not in old pulsars. So this is more or less an idea, and particularly with the neutrons actually are committed in India actually. We are proposing some proposal to the next generation this radio telescope, square kilometer millimeter array to do this kind of observations and to know more about this superfluid phase inside neutron stars. Okay, so this is much talked about by Stoker in this talk. Only thing I want to take one specific comment about this: the matter created in heavy-ion collisions is very short-lived, whereas the matter inside neutron star will survive for 10 to the power 9 years. So as a result, the matter in neutron star in weak chemical equilibrium, that means in chemical equilibrium under weak processes. But in heavy-ion collisions, formed in heavy-ion collisions, there is not much time because it is happening on the strong interactions time scale. So there will be no such chemical equilibrium here. Okay, go to the next. So how to calculate this structure actually? It was shown by two groups, one by Tolman Oppenheimer using general relativity, that is starting from the Einstein equations with a specific metric, and this is the relativistic hydrostatic equilibrium, and this is there are two things, pressure and energy density. This is the equation of state which goes as input into these equations, and we can find out their structures. So here this equation of state V versus the energy density is shown. Three curves are shown here. One is the black one, which represents neutron proton matter. Second one, this red one, is neutron proton, and with one heavier barrier, strange barrier, that is hyperon. And next one is on the top of lambda hyperon. We add this Bose-Einstein condensate of negatively charged ions. So what you see, this black curve has steep gradient, so it is called the Stiffer equation of state. And with respect to this black curve, this other two curves has softer gradient. So they are called softer equation of state. And when we solve this QV equation with this, we get this actually sequence of neutron stars for this equation of state. And what you see is that if you have some exotic form of matter inside neutron star, then their mass is actually, maximum mass is 1. And this is highest for the neutron proton matter, then comes the red one and followed by the this. But what is the important point here, that they all actually satisfy the observation limit, that is the highest observed neutron star mass, that is 2 solar mass neutron star. Okay, next important event using this neutron star happened. This event in gravitational wave emissions from the collision of two neutron stars in a binary. This was recorded on 17th of August 2017. And if you remember this picture, orbital picture, two neutrons are going around each other. So the last few orbits actually here, so this is frequency versus time, frequency of the gravitational waves in two detectors in LIGO and Ford and Livingstone. This is Virgo. Virgo, there is no signal here, but you can see the signal quite, it is just the last few orbits, it is going around this neutron star, and their frequency is slowly increasing, and at the marker point it goes to LS. So here you can see this handport actually, only you can see very close to it, but here you can see the last few orbits actually. Okay, and what happened? This was not actually observed in this neutron collisions was not only observed in this gravitational waves, they were also observed in light. So there was an alert after these collisions here, and you can see almost these are the detector system, and in space actually these are observatories in space like Fermi, GBM, then you have integral of these things. So these vertical lines where the margin at the point actually, there is no activity, but 1.7 seconds after the margin, there we can see all these detectors shows a big actually. This was the recording of short gamma ray burst less than it existed for less than 2 seconds. Okay, so there is more of it actually. So this is the source in the galaxy NGC I think 4999, and they are all these ground-based actually detectors were geared up. Actually, they got all these electromagnetic signals from this margin. So initially, 11 seconds and 11 hours after this margin, first it was observed in blue and ultraviolet light. Next, it was observed after 2 days, that is in infrared, and followed by X-ray etc. What you see here on the right hand side is velocity as a function of time, and you can see that there are some predictions that a kilonova will be formed in this neutron star margin. Now, what is this kilonova? Nova has luminosity of the order of 10 to the power 39 arcs per second, and for kilonova then this number will be 10 to the power 42 arcs per second. And these blue points are all these observations, and red line is a theoretical prediction. So you can see that how nicely they are going hand in hand, and you can see also these predictions for this maximum luminosity for this, which is close to 10 to the power 42 hours per second. Okay, so what all these blue, red things light actually imply for this margin? Okay, so this is the after the margin, a remnant was formed, massive remnant was formed. Then around this, which is denoted by this yellow actually sphere, around this two dark yellow regions, this is the accretion disk actually, because when it was collided, like heavier collisions, matter were actually emitted in the equatorial plane as well as in the polar directions, and matter which could not go out of this actually influence of this gravitational field, they form this accretion disk. And we can see this ejected matter actually, this blue and red. Now, this is shown as this Y means electron fractions. What does it mean? Electron fractions means you have equal proton fractions, and that means that proton fractions plus neutron fractions is 1. So low electron fractions means high neutron fraction, and medium means, okay, so medium neutron fractions there, and high electron fractions means very low neutron fractions. Now, this was predicted by Latimer and David Schramm that when this matter actually is ejected from these collisions from 2 neutron star or 1 neutron star, 1 black hole, this will expand, and there are lots of actually free neutrons. And there are seed nuclei. They will be rapidly captured by this seed nuclei, and this process is known as R process or rapid process. As a result, new nucleosynthesis will happen. So, in supernova explosions, we know that we can synthesize actually our nuclei are synthesized up to the ion. But in this case, heavier nuclei will be synthesized. For example, in this case, this lead actually case. So I want to correlate this this blue and red with these colors of the light that I showed you, ultraviolet, blue, and infrared. Now, particularly this medium Y infractions component of matter, ejected matter, there are actually there are nuclei which are, I think, in the mass range of iron. And their velocity is less. As a result, light will come out first from there. Whereas in this red region, this lanthanides are solved because and those elements have higher velocity. So light will take more time to come out of it. That is why we saw first this blue light, and later this faded out, and then 2 days after we saw this infrared light actually. So that is why these two components. Okay. And what we learned from all these things actually, this is a chart. Mass is a very accurately measured quantity. Sorry, there will be a solar mass 1.186, and 2 neutrons masses involved in this binary collision was 1.18 to 1.6 solar mass, and total compactor, the debris that was formed after the merger, it has a mass of 2.73 solar mass. And amount of ejected material actually was of this order 0.05 to 0.07 solar mass. Okay. Now, another most important thing was discovered in these things, measured of these things, is the tidal deformability. What is this tidal deformability? So under the tidal influence of one neutron star, other neutron star will be deformed, or vice versa. As a result, we can write down this tidal field as epsilon ij, and this actually gives rise to this deformation qij, and this proportionality constant is called the tidal deformability. And if you can see that this from this tidal deformability, one can define this log number, which is written in terms of the areas of the neutron star to the power 5 times this of this constant and the tidal deformability proportionality constant. And if we express this in terms of this dimensionless quantity, so it is R by, we make this dimensionless, dividing it by mass to the power 5. So this was a measurable quantity, tiny quantity. It appeared in the fifth post-Newtonian term. So it is very small quantity. But what is the implications of that? Implications is this, that this tidal deformability actually connects to the radius of neutron star. There is another way to measure the neutron star radius. And here actually the neutron star radius measured was, it is 10 kilometer to 13 kilometer. So Nyson experiment gave us this neutron star bandwidth, that is 11 to 14 kilometer. Here it is 10 to 12, 13 kilometer. So what does this actually data imply? So this data imply that the Nyson case, we need a stiffer equation, whereas in the gravitational wave case, it is a softer equation. So though there is an overlap, but there is some tendency for these two measurements. Okay. Now I just next two slides, and so we talked about this ground-based detectors actually, which are measuring gravitational waves, and okay, so there will be more observations with the detectors in space, and there will be other actually where we do not need detectors. Pulsar will act as detector, gravitational wave detectors. So this will be a fascinating thing, and you can save billions of dollars, euros, or pounds. So particularly my focus will be this pulsar timing actually. So our baseline is actually full of this background stochastic gravitational backgrounds. And these are coming from various sources like supermassive black holes or maybe inflations. So all these things. Now, let us see this experiment. So this is the experiment, pulsar timing experiment. What is pulsar timing? So from the Earth, observer is measuring the pulses at regular intervals. So this is the pulsar timing technique. So here you can see a network of pulsars. So these pulsars now, when this stochastic gravitational wave background is passing through these pulsars is delta 1, there will be a delay in the actually arrival of the pulse from the pulsar to the observer. But that is not enough. So it could be some spurious effect, it could be some other things actually which might not be related to this gravitational wave background. So then what one can do and understand that really these pulsars detected some gravitational waves. So this is a particular correlation called Helling-Towns correlation. Now what is this? Suppose there are, we should have some 10 pulsars. Pulsars are very stable blocks, particularly millisecond pulsars. So these millisecond pulsars are recycled pulsars because after the lifespan of a pulsar or neutron star, it goes to the gravity. But again, if it is in a binary with another companion, then it actually matter and then spin up. So these are old pulsars and very stable blocks. Yeah, I am done. So there should be some correlations there. This correlation is shown at the bottom, and the angle between these two pulsar 1 and pulsar 2, this zeta is shown here actually, and this correlation is written in terms of this angle. So this is the correlation as a function, so the plot of this as a function of this angle. So all the pair of pulsars in the network would show this kind of correlations. Then there will be detections. So there are 4 such actually experiments right now going on in USA nanograph. This is European pulsar time. This is pulsar pulsar time array that is in Australia. And the new actually entrant into this picture is our Indian pulsar timing array. Okay. And so this Indian pulsar timing array is using this upgrade